Welcome back to the post-lunch session. So we have with us Mr. Nikhil Sonawane. Uh, he is associated with MathWorks based out of Pune. He works with academic institutions, helping them out with MATLAB and Simulink. He has more than 10 years of experience with MATLAB, and his technical expertise lies in the field of machine learning, signal processing, communications, and hardware integration. He's done his BSc in Electronics and Telecommunications from Vishwakarma Institute of Technology, Pune, and his master's degree in Biomedical Engineering from Indian Institute of Technology, Bombay. I now request our head, Department of Mathematics, to felicitate him with a small token. Okay, so the stage is all yours, sir.
Hello. Yeah. Thanks, ma'am, for the warm welcome and helping with the introduction as well. So as I was saying, mostly we'll be talking on how we can solve ordinary differential equations or partial differential equations more effectively in using MATLAB specifically. And so before we get into it, I'll just quickly go on the overview of what exactly MATLAB. But before that, may I know how many of you have used MATLAB somewhere or the other, maybe in research or teaching or just somewhere? Yeah, ma'am, may I know where have you used it?
For engineering students, usually we teach them all the basics.
Yeah.
How to evaluate things using MATLAB.
So basically the code scripting and everything,
Yeah.
you have used it for
like
that.
To solve equations versus
Okay.
equations.
Yeah, anyone else who has used it before? Here, yes ma'am. Have you used it? Okay. Anyone? Anyone from the online participants that we can see? Maybe you can put it in the chat itself. Okay, so I reckon that most of the participants over here are very new to MATLAB. So what exactly MATLAB is? So MATLAB is just like any other scripting tool. It's used for programming, as it is mentioned. It is a programming environment basically, used for data processing, analytics, can be used also for computations or create different models. So basically it's a So basically it's a scripting tool where you can write lines of code depending on what your algorithm demands for. Okay. Again, it has a lot of advantages over other tools. I'm not getting into each of it. But there are majorly two tools from MathWorks. One is MATLAB that we were just talking about, and second is Simulink. So I won't be talking much about Simulink over here, but just to make you aware, Simulink is another tool. It's a graphical based tool where we create block diagrams of different real life systems that we have, and then we try to compute it. So in this over here you can see an example of a windmill itself. So how a windmill can be modeled and simulated, that is where Simulink can be used. So it's just a drag and drop kind of an environment. There are different blocks available. You can create your own blocks as well, and then you combine these and connect these blocks with each other to have your model ready, and then you go into the simulations and everything. So this is wherever model-based design approaches are being followed, Simulink is one of the major tools that is being used. So it might be from automation, in automation or aviation industry or any other industries. This particular tool is majorly being used. So these are some of the key industries where MATLAB and Simulink are being effectively used. So there are some engineering aspects of it over here which I have mentioned, but this is very much used in science as well for research and development. Math is one of the major areas. Because we are talking about math over here, when we see the logo of MathWorks specifically, does something come to your mind, like what exactly does that resemble to, or what exactly it is? Maybe this is the logo of MATLAB or MathWorks. So, sorry? Yeah, surfaces, but what exactly? Now this is also surface.
Three-dimensional.
Okay, three-dimensional surface, but what exactly, maybe if you can think of what exactly it is? It is a specific, maybe it is again a partial differential solution of a partial differential equation. But what exactly? Which partial differential equation? Okay, I'll make it simple for you. It's a L membrane. Sorry.
Parabolic.
So your voice is not clear.
Parabolic.
Parabola. No, not exactly a parabola. It looks somewhat like it, but it's actually an L-shaped membrane. So if you have an L-shaped membrane and if it is oscillating, if there are different waves created on that, it is one of the snapshot of that which has been taken. And it comes from the founder of MathWorks. So his name is Cleve Moeller. It is a part of his research. He was working on membranes, and MATLAB actually started off from mathematics. So that was the first, and then it went into different areas. But the birth of MATLAB was actually in the field of mathematics and more on differential equations. So that's the history of the tool. So coming back to the topic. So this would be the agenda for today. We'll talk about, quickly go over the introduction. We'll see what live scripts are. Then we'll see how effectively MATLAB can be used for solving both PDEs and ODEs. And at the very end, we'll have resources and Q&A session. But before that, getting into the topic now, what do you think are the major difficulties that you face when trying to teach differential equations? Before that, maybe can I have a show of hands on how many are professors or teachers over here? Okay, that's the majority of chunk. And how many are researchers? Okay, and I guess that's all right. Yeah. So for the professors maybe and for the researchers, you can think of when you're in your research, when you're modeling differential equations, maybe what are the major challenges that you face? Or professors, when they're teaching it to the students, what are the challenges that comes to your mind?
Visualization.
Exactly, one of them is visualization.
Differentiating kernels.
Okay.
Otherwise, it will take more time to differentiate.
Yeah, so basically what you mean to say, I'll put it in different words. Well, when we are using the pen and paper mode for solving differential equations, it's difficult to visualize and perceive what exactly is happening. So for example, when I was learning electromagnetic waves, it was very difficult for me to actually understand how the wave is moving, how the electric field is going and how the magnetic field is going and all those things. So again, and then there are different operations that we do on these three-dimensional entities, like finding the curve of it or maybe finding divergence and all that. So it becomes difficult to perceive for us, and that makes it even more difficult to understand what exactly it is doing. Maybe we'll be able to solve it on paper using the analytical ways, but it becomes difficult to like understand more of it. So let's see how we can solve this particular problem in MATLAB. So I'll directly go to MATLAB. But before I get into the ODs and PDs, and there is just one fun thing that I wanted to show. So there is an app. This is again this is not an inbuilt app. This is a package that I have installed in MATLAB. And again, this was created by the founder of MATLAB, Mr. Cleve Moeller. So this is just an app. This gives different grids over here. Maybe I'll open this particular one. And let's see what exactly this is trying to show. So what do you understand from this particular graphic? What is this exactly? Sorry? Simulation of person walking. So how can you simulate a walking person? Nothing this mathematically. Yeah, that is we will have to change some parameters to show it walking and the graphic is moving and all that. But what is the heart of that? What is at the center of it?
The coordinates.
Yeah. Yeah, the coordinates are moving, but these points might be obeying some kind of equations, right? So what are those equations? Uh,
There are multiple straight line equations.
but effectively these are partial differential equations that are being solved, okay? Now depending on the constants, parameters and other things, the speed of it or the bounce of it and all those things will change, but effectively these are partial differential equations, okay? Now just by, and there are some sliders over here to change the speed and other things. So what will happen if I change the speed is just the recursion of these points will change, or I'll just quickly do that maybe. So the walking speed increases over here. So it's just at the back end there is some constant that is being changed, and because of that we are trying to have that kind of a motion. Or for example, I change this gender grid somewhat over here. It's not very clear over here, it is missing out on some of the sampling things because of my maybe laptop is taking up a lot of computations on Zoom and other things. But what exactly is happening, or I can share this with you, you can actually try this in your laptops, is the length of the body criteria that changes. If I take it on the left hand side, the length of the shoulders increases, and if I take it on the other side, the pelvis girdle size increases, and that is how the swaying and all those things can be demonstrated over here. Now this is it's very and that's the reason, like if you think about it biologically, a man's walk is different because the center of gravity is on the upward side, or whereas the female's walk is a bit different because the center of gravity has moved a bit down, and that is why the swaying and other stuff gets added. So this actually can be modeled just by using partial differential equations. I'll stop this. Again, there are different aspects. I can share this with you. So there is this waves part also. So this is one-dimensional waves. If I get into a square wave, so this is how square waves actually move. So this, when you are showing it to your students and explaining them how waves are propagating, it becomes much more simpler for them also to understand that actually this is how it works, and that creates an impression of how the waves are moving and other things. Again, if I go into the L-shaped membrane, so this is actually from here, if it gets even more elongated, then the MathWorks logo will actually get created. So just to give you a brief understanding on what are the different possibilities and how these can be modeled and used for teaching. So what I'll do is maybe I'll take an example and then try talking about it. So everyone might be familiar with the heat flow equation, right? It's a partial differential equation. It looks somewhat like this. Again, I'm not getting into the theoretical aspects of this because of the limitations of time. But this is how it looks like, and these are alpha is the thermal diffusivity of the material that we are talking about. So when we are trying to solve this now, or there might be an engineering problem that heat is transferring from the median, and you want to have an insulator in between so that the heat does not get is not flowing ahead. So something like that is an engineering problem that you want to model, or the thickness of that is what you want to model, or in two-dimensional space, or maybe I'll talk about that in some time. But now restricting our discussion just to one-dimensional thing. You want to stop that energy to move forward, so you're putting an insulation. Now you want to decide on what should be the thickness, what should be the material, and all those things, right? And then again, the trade-offs is that if the mass and other things might also be the trade-off. Which material is available to you? Again, those are the constraints and everything. So when we are just trying to solve it, I'm again for for the sake of time, I'm not getting into each and every line of code. I'll just demonstrate on what exactly is happening. So we decide on the smallest time step and the total time that I want to compute the entire thing for. So that is what it is doing. And then we are just creating some starting points or the temperature profile over here. And this is how the temperature profile is changing. So it starts from 0, it goes to a maximum of 800, and then again drops down and comes down to 0. So this is how my temperature is changing at one end of the material, and then how I want to see how the heat is flowing through the conductor. Okay. Now at the other end of the conductor there is some kind of a thermocol sheet that I am applying, so that to insulate that, or the temperature or the energy should not be moving ahead. That's what the problem is over here. Then I define what exactly is the thermal conductivity, density and specific heat. So all these are properties of the material that is being considered. Now depending on what material you are choosing it, again that will change. Okay. For now I am assuming that the thickness of that sheet or the thermocol sheet is 0.05, and then I want to see how or visualize on what exactly is happening. Again, then this is how I'm setting in and defining some parameters, initializing the graph, and the main part over here is how I'm going to solve it. So the way that I'm using it to solve this is forward differentiating method. So basically we assume the entire material to be just some nodes, and from one node to other node how it is approaching. So it will pass the energy to the adjacent node, it will pass all the energy also to the upward adjacent and downward adjacent and so on. So that's how the energy will be flowing, and that is what is governed by this particular equation actually. Okay. Again, there can be different solvers that can be used over here. We'll talk about that when we'll be talking about two-dimensional heat transfer. And again, this is just some lines of code to formulate that particular equation that we saw. So this was the equation, and this is what we did. Okay. So I'll just run this particular script. So you can see that how with time increasing, how the temperature is changing at that particular point. So heat is coming from that particular point, and then how the temperature on that boundary is changing and how it is impacting the internal points on the conductor. And here is the point at 0 where I am keeping my insulator. So finally if we see, it's somewhat like this. So because our temperature profile was like this, it eventually dropped down. So because now at the very end it is at 0 here, but still the temperature at that particular point is not 0. So this is at t equal to 2000 seconds. So you can see that the temperature outside is 0, but still there is some energy that is being transmitted, and that is why we got this thing. Now assume that there is some person sitting at the most extreme this particular point. Okay. Now at maybe 130 degrees Celsius or something, he is going to get fried out, right? So if assume that there is a problem that you want to have, where a person is there in that particular cabin or a chamber, and you want him to be alive. So this is way too high. Now you will have to either change the material or increase the thickness of that particular thermocol sheet that we are using, so that the heat, this should be in the operation maximum 60 is also too much, but for a split second 660 can be managed, but 30-40 is the max bearable temperature that I would say. So that is how again the problem can be depending on the application. And then if you want to plot the temperature profile of it on the surf plot, I'll maximize this, so it would somewhat look like this. So on this axis we have the time, this axis, here we have the position, and on the z axis we have the temperature. So how the temperature move, this is basically the temperature profile with respect to time. So again, the outer temperature, how that was moving. So this is what we defined. This was the input that we gave, and this was the inner temperature graph that we can see. So how it increased till time t equal to 2000 seconds. So it gradually increased and then saturated somewhere around that. Yeah, this one. This is at the other end of, that is the problem statement, that is the input that we give. So that was, it is the initial. Initial is actually 0 and the temperature was increasing till this particular time. So that was at the other end, and we are observing what happens in the semiconductor sheet, sorry, thermocol sheet that we have. So we have that the final temperature that reached inside, that was 137 degrees. Okay. So now this is just one of the examples that we can see for modeling of partial differential equations. So for people who have used MATLAB before, does this particular sheet that I am showing, does this look different, or is it the same that you have used prior? Sorry?
We are not used for partial.
No, anything that you have used prior. Yeah.
Matrices and all those.
Yeah. But do you see some difference in maybe the text being over here or the equations? Okay.
Jumps and all are the same.
Yeah. So so this is actually the live script that I am talking about. So there was a traditional script of .m script. .m script somewhat looks like this, and then we just write in quotes over here. So this is how the traditional scripts in MATLAB look like. And if we want to have any comments over here, this was the only way that we can have it. Okay, there was nothing other than this, and nothing fancy that we could do over here. But when we talk about a live script that I just mentioned you, this you can see that there is a heading to it, there are equations onto it, there are then codes again. So what we can, so if I go over here and click on new live script, so this is the gray part you can see, that is the part where you can actually write your code. So that is again the same bit that I can write, and so on. And then if I want to have some text, there is an option of so if I go in live editor and click on text, so now this is out of the gray part, and then I can write any text that I want. And then I can have headings over here, I can change the font and everything, whatever you can do. Most of the things that you can do in Word can be done directly over here. We can have equations, we can have images as well. And whatever you are running, any output that comes in can be directly printed over here itself. Now, initially it was that we would have to go to the command window, or the figures might pop out and all those things. So here there is nothing like that, everything can be seen at the same page. Now why I am specifying on this is from a student's perspective. If they are doing any lab experiments, for example, they just have to perform this, have entire theory, images, outputs, everything at the same page, have the code also at the same page, and then there is an option of actually exporting this, export to PDF, and then the entire script with the outputs, with the code, and with the theory that has been put can be created as a PDF and be shared with the instructor. From the professor's point of view, imagine teaching MATLAB and then having a PowerPoint presentation also, and then juggling between these two. That also becomes a difficult task. So you can have the entire PowerPoint details into the live script itself, and just use the live script the way I used it right now. I didn't go back to PowerPoint. So that is one of the major advantages of using live scripts in MATLAB. Now this has come after 2016, so any version that you use from 2016 onwards, you will be able to use live scripts. Any queries on this particular aspect till now?
Hello.
Yeah.
Sir, can we upload the live data to this platform?
Yes, we can do that, sir. There are different ways. It depends on from where you are going to upload it, what is your source that is coming from, and depending on that, there are different ways to do that. So if you can elaborate on your problem, maybe I can help you better.
Like suppose I am trying to download and use some data from Yahoo Finance. Okay, it's a time series data of some stock market indexes, and I want to do some analysis. So how I can do that?
Definitely that can be done directly. We can actually point MATLAB to the websites where the data has been populated and can be pulled from there. So if you can just mail me directly about your problem statement, maybe I can help you with the resources that are readily available.
Okay.
Yeah.
Okay, sir.
Thank you. You had something.
Yeah, can you write it with a stylus on it?
You can create an image of it and put it over here.
You can insert images.
Yeah, JPG images, TIFF images, everything comes over here. Equations of LaTeX can also be put in over here.
Is it open source?
No, this is not open source. MATLAB is a proprietary source.
Is there a similar version? Is Scilab a similar version?
Scilab is a similar version of it, but it has limited functionality. It doesn't have the support that how MATLAB and its toolboxes are, but it's the most nearest open source counterpart to it. Maple, I don't have much understanding of that. I haven't used it prior, so maybe I'll have to check on that, and then maybe I'll get back. But what we have like interacting with majority of the professors and academicians that we have heard is for visualization and other things, MATLAB is one of the major tools, and that gives some, like with minimum effort, the visuals that or the images that are being created, the surf plots and everything, those are very high quality, and actually researchers are directly using these images for their paper publications and other things. So that quality of images are being generated here. So the way we saw one-dimensional heat transfer, just quickly going over the two-dimensional one now. So now assume that it's a two-dimensional space. So just to give you an a quick example of this, assume that the spacecraft is coming from space and going to enter into the Earth's atmosphere, right? Now it is coming at huge velocities, and that is the reason it will experience a lot of friction on all the walls of the spacecraft, right? And because of this, a lot of heat is going to get generated. Now the task is that the aircraft should not get burnt when it is entering back. So that's the problem statement. Now for that we'll have to design the tiles and thermocols and other things over here. Now depending on because we don't want to add a lot of weight also onto the aircraft because it's going and traveling back. So that is also one of the constraints. So the temperature, so the material that we are going to use should be the thinnest possible case over here. So all those things are the constraints. And if there is any damage to this, or if this doesn't function well while coming back into the Earth's atmosphere, the spacecraft is going to just get into pieces because of bursting or due to fire. And that is what actually happened in the unfortunate incident of when Kalpana Chawla was coming back in her spacecraft. So this is how it becomes, such problems get critical. So we can think of that as what we are modeling right now. Just there is a spacecraft and then it's coming back into the atmosphere. Again, there is a temperature profile that is being given. This is how it will increase and decrease, and the time step that over here. So any ordinary differential equation or partial differential equations, when you try to solve it, there are two ways to go about it. One is the analytical one and one is the numerical one, right? Analytical one is only possible for specific equations, because where we have defined the integrations or differentiations, or where we actually can write a pen and paper form of it and then try to solve it. But it's not always possible for practical cases. And then there comes in the numerical solutions, and when we are talking about numerical solutions, these are not the accurate form of it, but somewhat an approximate form of it. So what we do is we try to compute a particular time step, we try to go ahead in time for some instance, and then try to compute for that particular time instance, and so on, and that goes on. So now what will help us to compute that time instance, that particular data, is what we have from the previous data set and the current changing information, right? Now, this is how, and depending on what exactly is the solver that we are going to use, it depends on what is the accuracy levels and how we are going to model that particular example. Okay, so that is why the time step over here and the solver is the crux of solving any differential equation. Now, if you are going to get a very simple solver, if that is going to do your job, but the same solver may not be able to do a job in other partial differential equations where you need more accuracy. Or if you change the time step too much, or if you take the time step too much, the computations are going to decrease, but the calculations and the result may not be accurate, because every error that gets introduced over here is going to get accumulated. There will be a compounding effect. So if your t equal to 1, you are computing from t equal to 0, and then if there is an error in t equal to 1, while computing t equal to 2, that error is going to get carried forward, right? So that is why the time step and the solver plays a very important role in solving any differential equations. And that is why we are defining it over here. Now, depending on the application, it may increase or it may reduce. Now, reducing it is most of the time, reducing it is going to give accurate results, but it is also going to add to the computational overload that you are having. So it is going to pull up more computational power. Okay. Again, this is just plotting and other things that I am doing over here. Here is again the solver that I am using. Again, I am not getting into the details of it or the theory of it, but there we have put the option of adding solvers. Now, this is only possible, something like this is only possible to be done in live scripts and not in the traditional scripts that we have. So, and again we set the grid sizes and everything and other things. Again, the properties of the material we are defining here, and then we are just trying to solve that. This is the algorithm that is being put into. So I'll just run this. There is some error that we got. So it is actually able to show you, so it's still changing, and you can see the temperature profile of it, how it is changing with time. So it is getting accumulated and it's actually solving the particular partial differential equation. So it's basically a two-dimensional surface, and how the temperature is changing on that surface, that is what we are trying to see over here. So again, depending on which solvers you use, what is the time step and everything, your accuracy levels and how your model is going to behave is going to vary. So I'll just stop this because it will take some time. There is also one more way to do the same things. I started off with an app that was actually created by someone, but you can also actually create apps in MATLAB. So the same example, if we try to see, so this is actually the same algorithm has been coded into the app. You just see the graphical user interface and then try to visualize this. And this can be used as a great teaching aid where you don't want students to have the code understanding, but you want actually what is happening on the outer side, or just a high level understanding of that. And this is the app designer. So if you can just, and this is just drag and drop. So if I want access onto my app, I just drag and put it over there, so that access will come. So the graphical part of it, like what should be the dimension, or where exactly should be the access and all those things, that you don't need to code, that automatically comes in. If you go click on the code view, you will have to just focus on the algorithm that you want to have. So what happens when you click a particular button, what should be running at the back end, and so on. So that you will have to code over here. Other things, other graphic related aspects automatically get populated over here. So if I just run this, so this is the app. Now you're not seeing the code part of it, depending on these particular aspects. Now this is the 1D simulation. I just click on it and you can see the same thing that we did in the live script. Now this can be used as a great teaching aid when you want to make them understand how the temperature profile is changing. What happens at this particular, now it's still changing to some extent. So it will go till 2000. And this is the other graph that we get. So this is the boundary temperature, the dotted one, and the inside temperature is this one. Again, changing these parameters will again change the graph and how it is getting solved. So it is also telling what was the highest temperature that was reached inside. Same can be done with two-dimensional as well. Because now it's a two-dimensional thing, it's a surf plot over here. So it will take some time to populate, but meanwhile, any queries on this particular part? This might be a very high level work or session because we are not getting into the theory behind it. It's more focused on how these particular equations can be modeled and how this can be actually, the visualization part can be made easy. So that's the whole focus of this particular session. So this is again, we got this particular graph, the boundary temperature and how the inside temperature is changing. So any queries on this? Yeah.
Are you using any libraries for the codes?
Everything is inbuilt in MATLAB.
That's all.
Yeah.
And what is the syntax?
Syntax for writing the code. So it's actually, this is what the code is. So
So you don't have to define any variables.
yes, they are defined actually. If I open the code, this is all the code that I am running. So you'll have to define, like depending on your application, you have to define what exactly you want it to do. You'll have to define variables, you'll have to define your equation, and then you will have to define, as I said, the time step and the solver as well. You will have to code it. If it is an inbuilt solver that you want to use, If it is an ODE, maybe ODE 2, 3 or ODE, any other ODEs that you saw, or if it is a stiff equation, you will have to use the stiff solvers and other things. So again, depending on what your problem is, definitely there will be some solvers that you will have to put into. You can use inbuilt solvers, you can use your own solvers.
So is it necessary to call up those servers right before you begin the coding, or we can call it up anytime?
We can call it up anytime. So now, depending on again how you define the problem statement, in this particular one, I was defining it over here. So there was a variable that I created which took in my whichever I select over here, that will be selected and that function will be called. So that is how I have coded it over here. Any queries on this? Anyone from online? Yeah.
I just saw that rank recursion method there. So is that you input those initial values you do not input in that particular way when you code it up?
This one you are
Those
saying?
initial values how to calculate for
So these are the initial values that we are actually setting it up.
yeah. Okay.
So initial point that you will, for any differential equation where your starting point you will have to define it. That will be a hard coded thing. The next steps where you want to start and what would be the subsequent steps that is the solver is going to take part, can compute that.
So that is even repeated steps.
Yeah. So it's going to compute. It's like at t equal to 0, it's the initial condition or the boundary conditions that we define in any equation. And with those equations, the solver or your equation is going to perform the next steps. Yeah.
And that graph that you had shown, it had some uplifts, right?
Yeah.
What does it indicate that the temperature is not increasing at that moment of time?
So basically, when we are talking about one-dimensional heat transfer, the graph was two-dimensional. It was just time versus temperature, right? Now, because it is a surface thing or a two-dimensional plate that we are looking at, the temperature is going to vary in x direction, it is going to vary in y direction, and there is a time aspect also. So there is one in the time. There is x, y, and temperature. So at what time, at what point on that plate is my temperature changing is the graph of it. It's basically the spatial change in the temperature.
Okay, that's a gift
Yeah.
section.
Yeah. So with that, maybe we'll take one step back. We'll talk about ODEs now. Because when we are teaching partial differential equations, the first step that we do is starting from ODEs. Because our professors are started in the other way direction, because the theory and other things I didn't need to touch on. So when we are just take an example, just a very basic example of a projectile. Okay, we throw something in the air, it comes down, and there is a parabolic path that it follows, right? This we have been learning since like many years now. We have also in 11th or 12th we actually find all the equations of it and all those things. But there is one assumption that we always took in that particular solving all and taking those equations is one, the air density is not changing, and we always assume that it is a vacuum related. We are doing that in vacuum, and that is why we got a perfect parabola. But now assume that it is a spacecraft kind of a thing, or we want to launch some satellite into the air. It's not going. There will be air, and there will be some air drag onto it. There will be change of density of air, and because of it, because the density is changing, the air drag is going to change, and all those things. So now, if we were to have these parameters also considered, the traditional Newton's laws are not going to work over here, because there are a lot of assumptions into it, and then you will have to define your own solvers and then try to compute this, right? So now taking this example and this as a starting point, let's try to see how we can model this. So So this is the traditional thing that we have been learning. This is applicable only and only when we are talking about vacuum, and there are all other, we are just assuming a lot of things over here. Okay, but when when we are considering air drag, the entire equation starts changing, because there is air drag which is proportional to the velocity square, and again the velocity is in both direction, x and y. So there will be a component of air drag which is coming in x direction and y direction as well. Okay. So the only thing that we can define to start off with is these particular parameters: the initial velocity, mass of projectile, area of projectile, and so on. So that is the coefficient of drag and density of air. Okay. Now here I am assuming the density to be constant. I am just assuming the air drag is changing, because air drag is proportional to velocity, and velocity is changing throughout the entire path. Okay. These are just again initial bits that I am defining, and to solve the ODE, because this is a first order ODE, the way I am trying to solve it is using the state vector method. So I define this z and dz. So z is a vector which has y, velocity in y direction, again x, and velocity in x direction. Okay, so this is an array. Now this is not just one value of it, it's going to, so it is at t equal to 0, I am having these values, so there will be 4 values. At t equal to 1, there will be again 4 values, t equal to 2, again 4 values, and so on. So this will go from t equal to 0 to t equal to n, that I am trying to solve. And again dz is the differentiation of that, so this is y dot, vy dot, x dot, vx dot. Now again y dot can be replaced as vy, and x dot can be replaced as vx, because derivative of displacement is velocity. Okay, so now with this information, so what exactly this is? So for example, I want to compute at time t equal to 1. I have information of the previous instances only, right? So I am using dz and trying to compute this. So if we look at Euler's method, what does Euler's method say is that y at the present value is equal to gradient of that into the past value. Okay, so to start off with, what we'll do is we'll try to use the Euler's method over here. So it's the present value is equal to previous value into, present value is equal to past value plus that addition that we are doing is gradient into the previous value. So we'll try to do this for each of these. We are trying to apply the Euler's for each and computing y, x, velocity in x and velocity in y. Okay. So this is how it has been defined. So the main script that I am talking about is having parameters that we set, the constants and other things. We select the solver. For this instance, I am just selecting Euler. And then which one we want to select is this, Euler, Agekut, or anything else. And depending on what solver I choose, that particular file will be computed. And that is how the structure is. Any queries in this particular thing? Yeah, you can have your own. So this, anything you can put in. You will have to code that piece of code, that piece of algorithm. You can use your, it's just that this is running, then this particular solver is running, and then it is passing the pattern to it. No, this actually I am hand coded. I have written it, that entire code for Euler, for Agekut.
Now you are selecting. So that means it is written and you are bringing it in.
No, that is there in this particular folder. I have written it hand coded. I am not using a pre-defined package. So the way I have written for Euler or Agekut, you can use your own solver as well. You will have to just put it into that file and call that function.
Which programming language is it? MATLAB?
It is MATLAB.
Base language
Base language, it's multiple languages. Java scripts are there. There are some part is written in C as well. But what we are writing is everything MATLAB. At the back end, what happens is that's a different story. We don't have to change that particular aspect. Yeah. So here basically I am selecting the solver. So 1 being Euler, 2 being Agekut, and 3 being variable job. So I have defined it in that way. So if I open this script, so again I am just defining the horizontal states and everything. and this is what my part is. So if solver 1, I'll be using the one step Euler function. If solver equal to 2, it is one step Runge-Kutta. If solver equal to 3, one step Runge-Kutta 5. So these are the functions that I have created, and depending on what I am putting in that number, that particular file is going to execute. So this is what the Euler state. So once I'm selecting that Euler file, or once that solver equal to 1, it will go in this particular file. And what I'm doing is I'm just defining that dz that I'm getting it from the main script. I'm just taking it over here and I'm defining this. This is just for the Euler, because Euler is defined in this way. The present state equal to previous state into gradient into the time step that we are having. So that is how it is defined. So it's just a one line thing that we are doing. Now remember that z has x, y, velocity of x and velocity of y. So it will be it is it's an array basically, an array for each time step. So it is going to compute this for each time step for 4 variables. Okay, so it has all that data, and once this is done, this is passed as the output over here, and then that will be given back to the main script. So I'll just quickly run this. So this is how the trajectory is now. So what we had as a parabola, every time that we think of, it's not exactly the same. It's skewed on the right hand side. Okay, because initially the velocity is very high, and that is how it is going there. It's skewed to the right hand side. And if we plot other parameters, maybe we can have this. So time versus horizontal distance, time versus horizontal velocity, time versus vertical velocity, and time versus again its vertical distance. And this is how the density is also changing with time, with the altitude. So as in how the altitude is increasing, the density is low in the initial bits. It's as it is going up, the density is dropping. So this is for Eulers. Again, similar things can be done for Runge-Kutta as well. There is a script, I can share that with you. I'm not opening that right now. What I want to show you over here is, so this is what we did. So we calculated the same problem statement using Eulers. We computed the same problem statement using Runge-Kutta. And then now we want to compare what are the differences. So the major difference comes over here. So this is just Runge-Kutta, normalized error versus time step. But this, if we observe, I'll maximize this maybe. Just quickly run this. So if you look, this is a logarithmic graph on both axes. So if you look for, this is like increasing time step, and this is the percentage error. Okay. Now if you look that for larger time step, anyway both are same, but the error is also more. Okay, because the time step has increased. Now, now if you look into this particular bit, the majority of our applications are going to be over here or here, because time step, it should be computationally possible as well. It's not too much heavy on the computation, because reducing it too much will create more computations, and it should not have a lot of error as well. So if you compare both aspects, so this one is Euler and this is Runge-Kutta. So it's a huge difference. Even if you have the same time step for both, it creates that much of a huge difference. So now it depends on what is the application, where you want to use Runge-Kutta or where you want to use Euler. But this can be a great tool to teach students the differences of Eulers and Runge-Kutta and how it can be extrapolated into real life applications. Basically the comparison between it. Now this can be done for any solver the way it has been done over here. just to compare different solvers and everything. Any queries on this? Yeah.
See, basically Alice method and Ravikuta method, also iterative method.
Yes.
So when I do a program, like when I used to code it, like I used to give it as I steps, and then after 4 steps or 5 steps, where the 4 decimals match. I couldn't see that. Can you tell me where you have used that exactly? The solvers that you mentioned.
Yeah. So this is what you are saying, right?
Yeah. Because we put the formula and then we give steps to that. But
Yeah. So dz is another script
okay.
over here. So this is dz, and again when z is equal to greater than 0, this is now dz of second is the velocity of it, which is equal to k into z square. So z square is again velocity. So because it is velocity square, it is being mentioned over here, and this is what we are defining. So it is whether it is going upwards or coming downwards. That is what the if else statement is over here, and again this is for the y also. Just a second. Yeah, there is a loop. There is in one of the. Yeah, I got it. I got the question. It is there in one of the. No, it is getting over the steps. Otherwise, the entire.
One iteration and each step you are counting to get to this solution.
So there will be multiple iterations that are happening because we have defined it as 0.2 and we are going it till maybe. Sorry. It is there in one of the scripts which is getting called for sure.
Whatever you share will have all the results.
Yeah, it will have a delay. Yeah. Not a textbook of a kind, but this is what the file that I have. So all these are there on the website that I have called out. Everything is there. I'll talk about it a little bit. Yeah, this is the loop actually. So it's a while loop that is running. Yeah. So basically when z is greater than or equal to 0, so z is the vertical, z of 1 comma I is actually the vertical displacement. So till that I want to run this loop till it is greater than 0. So it is going, the initial point is anyway greater than 0 till the point it touches ground, and when it is crossing that and getting into negative, I'll stop the entire computation because it's not going to get into the ground.
Initial and final value both should be same.
Yeah, that's what I'm assuming because it's going. If it is going to start off from ground, I'm assuming again that it starts from ground, it goes up, it will fall down.
It's a projectile motion.
Yeah, it's a projectile motion. It will fall down and it will be. I don't want to compute it because that doesn't make sense to compute it after going and crossing the ground level. So that is why I have written the code in that way. Because if you use for loop, you will have to define how many number of computations that happens. But again, it depends on how much time step it is, and every time you will have to change that. When it is hitting the ground, you don't know after which iteration. So that is the reason I have used while loop over here. So with that, maybe I will quickly show this. Yeah. So now after this, if you want to start off with or understand how MATLAB works and the basics of MATLAB, the best place to start off is MATLAB on-ramp. I'll open the website also for you. But the best place is to start MATLAB on-ramp. It's roughly about 2 hours of a course. So and it is a very introductory. So everyone who is very new, anyone who is very new to it can start off from there. And if you have basic understanding and you want to get into the mathematical aspects, then there are some courses on math as well. Solving non-linear equations with MATLAB, solving ODEs with MATLAB, and so on. So any course,
sir, what is the URL for this?
yeah, I'm just opening in a bit. I'm coming to that. Just to note, any course that has an on-ramp word mentioned, that is available and accessible to everyone, because these are introductory courses of about 2 hours of each, and that just gives you an overview of that particular topic. But all other courses are a part of online training suite, which you will have to purchase separately, or it is available to you as on a complimentary basis if your institute is a part of campus-wide license. So I'll just open that. So it is basically, yeah. Yeah. So if you go into a browser and just even on Google, if you just find, if you search for MATLAB Academy, you will be pointed out to this particular page. In the getting started part, you will have all the on-ramps. There's maybe some internet lag over here, but you can find all the courses over here. Sorry, and depending on what your so you can search for this, just MATLAB Academy on even on Google, and then you will be pointed out to that particular page. So it has all MATLAB on-ramp, Simulink on-ramp, and other aspects. If you are working on machine learning, deep learning, wireless communication, and so on, so all those courses are also mentioned, are there, and all the on-ramps, as I mentioned, are freely available to everyone. So you can take up these courses.
Suppose an institute wants to arrange us more course for the other ones.
More
That
course,
are not online.
yeah. So either there are two ways. If it is on campus-wide license, then it will be definitely accessible to you. If it is not on campus-wide license and you are just looking at at those particular courses, then you will have to purchase it as a package of online training. So with that, I thank everyone for patiently listening and attending to this session in spite of a session after lunch and keeping it interactive. I would request everyone to just scan this particular QR code just to understand your feedback on this, and maybe if needed we can reach out to you. If you have any specific queries, you can put it in this particular form as well, and we'll try to get back to you as early as possible. And you can directly mail me as well. This is my mail ID. If there are any specific queries related to your research, or you need any support for any of your curriculum, you can reach out to this particular mail ID. Any queries, maybe we can stop for maybe 5 minutes or so. Even on online, if there are any queries. Sure. Yeah. I hope this QR code is accessible. You are able to open it, right? Even online part